Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 3. Applications of the derivative. Section 4.3. How derivatives affect the shape of a graph.
Lesson 3. Concavity and inflection points.
Part 2.
Well, before we leave this graph completely, although we've done everything that we were asked to, I want to make one extra remark, and that has to do with the type of critical number that we had for this problem. Back when we were doing part A, I mentioned that the critical number that we got here, x equal 1, which is a value where the derivative is changing sign, is a particular type of critical number. Remember, we said critical numbers are places where either f prime is equal to 0 or where f prime is undefined. And in this case, which kind of critical value do I have? When I plug x equal 1 into this expression, it makes the denominator of this fraction 0, and that means it's a place where the derivative is undefined in this case. So something kind of interesting happens at this particular local minimum. It's a place where the derivative is not 0. You don't have a horizontal tangent line. It's a place where the derivative is undefined. So if we go back to our graph here, you can even see that it's a cusp of the graph. I can see that there's no unique tangent line right at x equal 1. And in fact, we can investigate a little bit what the slopes of the tangent lines are as we come in towards that cusp. And it does make our graph slightly more accurate. So this was not asked for, but I'm going to add it as a remark. Let's look at f prime of x near x equal 1. Remember that f prime is the same thing as the slope of the tangent line to the curve. And f prime of x was this expression. Let's see if I can write it in there. It's 2 over 3 times the cube root of x minus 1. It's a cube root. And we saw that at x equal 1, it's undefined. But what happens close to x equal 1? So let's see if we can think about that a little bit. I'm going to allow x to get closer and closer to 1 from the right. So I'll say as x gets closer and closer to 1 from the right side, we're going to try to decide what happens to f prime of x, which is this expression. So f prime of x will be equal to 2 over 3 times the cube root. And as x gets close to 1 from the right, that means my x values are a little bit larger than 1. If we look at what's underneath the denominator here and think of x being a little bit larger than 1, something larger than 1 minus 1 is going to be something that is small. But what will the sign of that expression be? Positive or negative? If x is a little greater than 1 and I subtract 1 off, I will end up with something that is small but positive. When I take the cube root of something that's getting tinier and tinier but positive, I will get something that is positive in sign. And so this whole fraction, 2 over 3 times something positive, will have an overall positive sign. But what happens to the size of this fraction, the absolute value of this fraction, as the denominator gets tinier and tinier? If what's underneath the cube root is going to 0, 3 times that is going to 0. So the denominator of my fraction is getting tiny. The top is fixed at 2. When I have a fixed top and a tinier and tinier denominator, it means the overall size of my fraction is getting larger and larger. In other words, going towards positive infinity. Well, what does that mean about my graph? Remember that the slope of the tangent line is the derivative. So if f prime of x is going to positive infinity, it means that as I approach 1 from the right side, so as x gets closer and closer to 1 from the right, the slopes of the tangent lines here should be getting steeper and steeper, and I can see that they are. This looks like a steeper and steeper curve. And what's happening as I get right near x equal 1, those slopes are going to get closer and closer to a vertical slope. They're going towards a slope of positive infinity. So it means the type of cusp I have here is a very pointy cusp, and that it gets, the slopes of the tangent lines get vertical as I get right on top of x equal 1. My graph probably wasn't that accurate because it looks like the slope has some finite slope, but really the slopes of the tangent lines get very, very steep right in here, and so I have a very pointy cusp. You can check that as x approaches 1 from the left, the reverse happens in terms of signs. You're going to have a fixed top of 2. The bottom is going to be 3 times the cube root of something that's getting tinier and tinier, but let's check the sign. If x approaches 1 from the left, it means that x is a little bit less than 1. And if you thought about x minus 1, this expression, for a value of x that's close to but less than 1, then something smaller than 1 minus 1 is going to be negative. So you could get something that's small in absolute value but negative in sign. Well, you might first of all think, wait, I'd be taking the cube root of a negative number, but remember that's okay because it's an odd root. You can take the cube root of a negative number, you'll just get a negative number. So the overall sign of this will be a positive 2 divided by a positive 3 times some small but negative factor. Positive over positive times negative is an overall negative sign. And then think about the size, the absolute value of this fraction. You have a fixed top, a bottom that's getting tinier and tinier, means the overall fraction is getting larger and larger in size. In other words, in absolute value. So as x approaches 1 from the left, the slopes of the tangent lines are going towards negative infinity instead of positive infinity. Well, that should sort of make sense. As I come in from the left, my tangent lines, you notice, do have negative slopes. They're going down as I move to the right. And all we're saying is that the slopes of those tangent lines get steeper and steeper. Their absolute value gets larger and larger as I get closer and closer to 1. So what I have drawn here is really not quite accurate, because as I come into 1, I should be getting a very pointy cusp here so that the slopes of my tangent lines go to vertical. So that the true graph, if I were to just draw it over here a little bit more accurately, at least what's happening right at that local minimum of 1, the true graph should be something that is going to vertical right as I come into 1. And it's a very pointy cusp at 1. So that local minimum that we found at 1 is at a very pointy cusp, and the slopes of the tangent lines are going to vertical as we come in from either the left or the right. So I hope that that makes that particular graph a little bit clearer in terms of a small detail, but that was not really asked for in the different parts, the parts A through D of our question. So if you didn't think of looking at what's happening to f prime right at that point, you couldn't really be blamed for that, but it does make our graph quite a bit more accurate to know that it gets so super pointy right at x equal 1. Okay, well now I'd like us to go ahead and look at our last example, example 3, and we will investigate its concavity. So example 3 was on page 7 of this handout. It's the one of f of x equals x e to the minus x, and you may remember that we already looked at the overall rough behavior of the graph, where it's going up, where it's going down, and we found that it had one local maximum at x equal 1. So let's go ahead and see if we can look at the graph of that for a moment. That was on the next page, and see what we had so far for that function. So we had a local max at 1 comma 1 over e, which was about 1 comma 0.37, and we said the function is going up until I get to that local max, and then it is going down from then on. So whatever we add to this graph, we can't lose sight of this overall behavior. It has to go up, be an increasing function until I get to 1, and then be decreasing from then onwards. We don't want to destroy that information when we add in information about the concavity. Okay, fine. Well, let's go back and see if we can figure out what the concavity is. I'm flipping back to the previous page, and we're asking, where is this function concave up? Where is it concave down? Well, we said we have to investigate the sign of the second derivative to determine that. So I have to take the derivative of the derivative. So let's go ahead and write down what f prime of x was. F prime of x is this function. I suppose we could take the derivative at this point, but I think in this case it's actually a little bit easier to take the derivative from where we had it factored. I can see that I would need the product rule to take the derivative of this first term. So since I need the product rule down here, I might as well do it where I have just these two factors instead of two terms and a term that contains two factors. It doesn't make too much difference, but I'm going to go ahead and say, okay, this was my first derivative, and that's what I want to take the derivative of. So we're going to find f double prime of x, and I have to ask myself, what rule do I need to find that derivative? Well, it is a product of two things, namely e to the minus x times this other factor, x minus 1. So let's use the product rule. Remember how the product rule works. It's the first factor times derivative of the second plus the second factor times derivative of the first. So the first factor is e to the minus x, and I multiply that by the derivative of the second factor. Derivative of 1 minus x would be negative 1. Plus, so that is my f times g prime in the product rule. I should write down here that we're using the product rule. So this is my f times g prime. Now I need plus g times f prime for the product rule. So let's see if we can do that. So now I do my second function, which is 1 minus x, and then I have to multiply by derivative of the first, derivative of f. Unfortunately, it's a composition of two functions. I have the function negative x inside the e to the x function. So since it's a little more difficult to do and I have to apply another rule to find that derivative, I'm just going to use my operator notation and leave that for the next step. So far we've done f times g prime plus g times f prime, but this looked tough, and so I'm leaving it for the next step and just saying times whatever the derivative of f is. Let's go ahead and see if we can do this. I'm going to clean this up a little bit. It's minus e to the minus x plus 1 minus x, and now let's do that last derivative. Well, what rule do I need to find the derivative of e to the minus x? It's really got an inner function, namely minus x, inside the e to the x function. In other words, it's a composition of two functions, and so I'm going to need the chain rule there. So let's apply the chain rule. I take derivative of my outer function. But what is my outer function? My outer function is the e to the x function, and the derivative of the e to the x function, it's its own derivative. So derivative of e to the x is e to the x. If I leave it with empty parentheses where the x's go, it would be e to the whatever. That's derivative of my outer. I evaluate that at my inner function, and I can see the inner function there is just negative x. And now, by the chain rule, I have to multiply that by derivative of my inner. So it's derivative of the outer, evaluated at the inner, times derivative of the inner. And derivative of negative x is just negative 1. Okay, so let's go ahead and try to clean that up. I have minus e to the minus x for my first term, plus, let's see, negative 1 times 1 minus x e to the minus x. And I notice right away that both of these terms have a common factor of e to the minus x, so I might as well factor that out. And let's see what we're left with if I pull an e to the x out of this term and out of this term. When I pull it out of this term, I'm left with a -1. When I pull it out of this term, I'm left with these two factors. I'm going to multiply them out. -1 times -1. Well, let me go ahead and put those factors in, and then I'll multiply them out in the next step. So I've just pulled out my e to the minus x. So I have e to the minus x, and what am I left with inside the brackets? I have a -1, and it'll be plus another -1, so that's -2. And then distributing this out, -1 times -x would be plus x. So what does all that say? It's telling me f double prime of x is equal to e to the minus x times, and I'm just going to write these terms in the other order. I'll write it as positive x minus 2. It's just a nicer way to write f double prime. And you could also write these factors in the other order. Usually we put the polynomial factor first, but that's okay. So I'm going to go one more step here and rewrite this with all positive exponents. It's easier to analyze what your special numbers are if you write this with positive exponents. So I'm going to leave the x minus 2 in the top, and I'll make this exponent positive by pushing the e to the minus x into the denominator. It becomes an e to the positive x. Okay, so we have to decide what are our special numbers. And remember, the special numbers are any values where f double prime could be changing sign, where there's a possibility of it changing sign, and that's anywhere where either the numerator or the denominator of our fraction is 0. Let's think about the numerator. Well, I can see that the top is 0 when x equals 2, excuse me. So that is definitely a special number. What about the denominator? The denominator is e to the x. And I'm asking what value of x makes that equal to 0. We actually discussed that back when we were talking about the original function, because it also had a denominator of e to the x. And remember, we said that's always positive. You plug in a positive x, e to that number will be positive. You plug in 0, e to the 0 is 1, that's positive. You plug in a negative number, like -1, you get 1 over e, which is also positive. This is always positive, meaning it's never 0. There's no number you can put in for x and hope to get 0. So we actually don't get any special numbers from the denominator going to 0 because it never goes to 0. Our only special number is x equal 2. Well, let's put that on our number line. And I try to kind of line it up. So I had 2 right here on my number line, on the number line that was above for the first derivative. So I'm going to put 2 right in the same vertical position so that these two things kind of match up. Sometimes it helps to figure out what the graph looks like if those are lined up. And remember, we're checking the sign of f double prime to the right and the left of its special number, and it only has one, the number 2. Okay, so let's use some test numbers. I'm going to use my blue pen because my green pen is not sticking. So I'm going to try a number. Let me circle this. I'm going to try a number to the right of 2, such as 3 as a test value. I'm plugging it into this expression for f double prime. If I plug 3 into this expression, 3 minus 2, the top will be positive, the bottom's always positive, and so f double prime will be positive over positive, which is an overall positive sign to the right of 2. If I want a test number to the left of 2, I could choose something like 0. 0 minus 2 would be -2, so the top now is negative. The bottom's always positive, and so I get negative over positive. Overall sign is negative to the left of 2. Well, that means something about my original function f. If the second derivative is negative, remember that means that this curve f is going to be concave down. And if the second derivative is positive, that means that the graph of f is going to be concave up. Okay? So it's concave down for all x less than 2, and it's concave up for all x greater than 2. And what does that mean about the point at x equal 2? is it a place where the concavity is switching, where it's changing? It is. It's going from concave down and switching to concave up, unlike example 2 that we just did where it stayed concave down on both sides of its special number. Here it's switching, and so this is an inflection point at x equal 2. So when they ask for the inflection points down here, we just say, oh yeah, there's definitely an inflection point at x equal 2. If I want to know what's the corresponding y value, remember that you're looking for a point on the graph of the original function, and so you'd want to go back to the original f and plug into that to find the corresponding y coordinate. So there's an inflection point at 2 comma f of 2. Well, what is f of 2? I'll plug into this form of f of x. It's 2 over e squared. So that's 2 over e squared. So we have an inflection point at 2 comma 2 over e squared. Inflection point. And if you want to know approximately what that is for graphing purposes, you can plug 2 over e squared into your calculator, and I think that I did that somewhere here. Yeah, and I got 2 over e squared is about 0.27. So that's roughly where the inflection point is. Okay, so now we get to add this information to our graph and make our graph better. So go to the next page again, and let's draw in our inflection point. We had a local max at 1 over e, and now we're adding an inflection point at 2, 0.27. So it's not too much farther down than our inflection point was. So I go over 2, and I go up to a little less than 1/3 of a unit. So we have an inflection point at 2 comma 2 over e squared, which is approximately 2 comma 0.27. And what did we say about the concavity? If we go back to the other page, notice we said it's going to be concave down until I get to that inflection point, and then it flips and becomes concave up. So whatever it does, it's going to be scooped downwards to the left, and once I get to the inflection point, it is scooped upwards from that point on. So let's go ahead and see if we can add that onto our graph. I have to draw a graph that goes up until I get to my max and then goes down from there on. However, I want to have a graph, whether it's going up or down, that is concave down until I get to this inflection point and then flips and becomes concave up. So it has to be concave down forever to the left of x equal 2, and then to the right of x equal 2, it has to flip and be concave up. Okay. So I'm going to follow the green dotted graph, and here it's increasing, but okay, so we know that it is going to be increasing but scooped downwards until I get to this local max, because it's going to be concave, we said down, for all x less than 2. And it's, I should make this go all the way up to the 2 here. And it's going to be concave up from there on. So for x greater than 2, it is con up. So I'm going to follow the green dotted line, but draw something that is scooped downwards rather than scooped upwards. So it's got to look something like this until I get to that local max. When I get to the local max, it stays concave down, but now I have to follow the green dotted line and have a decreasing curve. And it continues to be concave down all the way until I get to my inflection point. So I'm going to draw something that is concave down, and it has to go through that inflection point. So it's concave down for all of these points until I get to my inflection point. whether the curve is going up, increasing, or whether the curve is going down. And you can see that this dotted line must be off because I have to go through this inflection point. But I have drawn something that is decreasing from the local max onwards. Now, when we get to the inflection point, it's supposed to continue to decrease, but the concavity flips. So now I have to draw something that's going down, decreasing, but flips to be scooped upwards rather than scooped downwards. So it's concave down until I get to this inflection point. Now it continues to drop, to decrease, but it has to be scooped upwards. Now, I've really only drawn 2 points on the graph, so it's still not terribly accurate. But we have a graph that is increasing till I get to the max, and then it is decreasing. And it is increasing and concave down, decreasing, stays concave down till I get to the inflection point, and now it flips and turns concave up. Okay, again, this is not a terribly accurate graph in the sense that we only have 2 points plotted, but it does have all the critical qualities of the graph on there. It has where it's going up, we know the exact point where it is switching and starting to go down, and we also know this information about the concavity, how it curves and curls as it goes up and down. Well, let's try to find a few more well-chosen points, and then I will make a little remark at the end about what happens to this function as x gets larger and larger. So we'll do that in a moment, but I think if we look at a few x values, this little remark that I'm going to make will make more sense as well. So let's go ahead now and see if we can think about what would be some good x values to choose. Again, we want to choose x values that are close to these interesting points that we've found, the maximum and the inflection point. We've only found 2 points on the graph so far. What do you think would be good points to choose? And you might choose slightly different points than I do. That's okay. Maybe x equals 0. Since we have an interesting point at x equal 1 and 2, I might want something to the left of those points would be x equals 0. And if you plug 0 into this function, remember the function is x times e to the minus x. That's my original f of x. Or you could write it as x over e to the x. That might be easier for the purposes of plugging values in. If I plug 0 in, I get 0 in the top divided by e to the 0, which is 1 in the bottom. 0 over 1 is 0. So 0, 0 is a point on my graph. So in purple, I'm going to put the actual points that are on my graph. So it should have gone through 0, 0, and you can see my graph is a little bit too low. Here's my maximum right here, and here's my inflection point. So we know all of those are points on the graph. All right, let's try another well-chosen value. I think I plugged in -1 just to get one more point to the left of our interesting points. When you plug -1 into this, you actually get -1 times e to the positive 1. So you actually get minus e as an output value, which is about equal to minus 2.7. So when I plug -1 in, I go down to about 2.7. And let me put that point in purple. So you can see this portion of my graph was not perfect, it wasn't too bad, but it should be looking like this. Just be sure that when you draw your final points in there, that you keep the same concavity that you had in your blue graph. So you can cross out your blue graph, but you want to be sure that this is concave down until you get to your inflection point. If you want to, you could plug in something between 1 and 2. My curve is supposed to stay concave down till I get to that inflection point. I think the next point that I plugged in was 3. And when you plug 3 into this, you get 3 over e cubed. Because you have an exponential function in the denominator, this is going to be pretty small. And in fact, it turns out to be the number 0.143. It's positive but small. So when I get out to 3, I'm only up 14 hundredths of a unit above here, which is actually pretty close to the x-axis. So this is sort of going down like this, but it will be something that is above the x-axis because this expression is going to be positive whenever x is positive. So I have a point that's maybe right here, and the curve is concave up, and I think I plugged in a few other values. So let me tell you what those values were. I plugged in 4, and if you plug in 4, you'll get 4 over e to the 4th. That's a pretty big denominator. E to the 4th is a large number. And you get 0.073 as an output. Well, where is that? It's even closer to the x-axis, still above the x-axis, but very close. So I have this curve that's scooped upwards. It's concave up. It is not touching the x-axis because this expression is going to be positive whenever the numerator is positive, but is getting very close to my x-axis. And you can see what happens if I plug in something like 5. Yeah, the numerator is growing, but the denominator is growing much faster. This is just growing in a linear way, 3, 4, 5, and so on. And the denominator is growing exponentially larger, and that turns out to be 0.034. So that's practically on my graph with this huge fat pen. That's practically on the x-axis, but it's still a little bit above. So my graph is getting very, very close to the x-axis. And you can keep putting in values here and just convince yourself. For example, if you plug 10 into this and figure out 10 over e to the 10, that turns out to be 0.00045. That's incredibly tiny. So when you're out here at 10, you're like almost on the x-axis. So let me ask you this question. As our x's get larger and larger, going off in this direction towards positive infinity, what is happening to our y values of these points? It looks like the y values are staying positive, but they're getting closer and closer to the x-axis. They are getting closer and closer to 0. At least that's what it appears. So we haven't really proved that, but it does turn out to be true for this function that the y's, I'll just write down here, as x goes towards positive infinity, the y coordinates are going towards 0. Another way of saying that is the line y equals 0 is a horizontal asymptote of the graph. So we have a horizontal asymptote right along the x-axis whose equation is y equals 0. The curve is getting closer and closer to the positive x-axis as x goes towards positive infinity. Now, if you happen to know Lhopitals Rule, you can actually prove that this limit is equal to 0. So I thought we would just take a moment and do that. This was not asked for in the problem, but I said notice also, so again, this is in the way of a remark, that we can actually find the limit as x goes to positive infinity and prove that this limit is equal to 0 if you happen to know Lhopitals Rule and have already studied that. If you haven't studied Lhopitals Rule, you will soon. So we're finding the limit of our y values. And remember, y is x e to the minus x. We could write this without the negative exponent and say that would be the same as the limit as x approaches infinity of x over e to the x. Now the problem with trying to find this limit is if you simply allow x to go to infinity, the numerator is going to infinity and the denominator is going to infinity because e to the infinity, as the input into the e to the x function gets large, e to that number gets larger and larger. So the denominator is also going to infinity. That was one of our indeterminate limits, indeterminate, which means not that the limit doesn't exist necessarily, but that we can't determine what the limit is in this form. Well, unfortunately, this is not the kind of problem where you can simply divide out by a power of x or something like that to find the limit. And it's true that the top is going to infinity as well as the bottom, but as we noticed over here when we were looking at these specific numbers, the top is going to infinity at a linear rate, at the rate of x, whereas the denominator is going to infinity at an exponential rate, much, much faster. So even though the top is growing to infinity, the bottom grows to infinity so much faster that the overall fraction gets smaller and smaller and goes towards 0. But how do I prove that rather than just noticing it numerically and guessing that the limit here is going to be equal to 0? I can prove it using Lhopitals Rule. If you know Lhopitals Rule, you'll know what I'm talking about. If you haven't covered it yet, you won't, but you will cover it very soon, I'm sure. So what I usually write is an LH here to remind myself that I am applying Lhopitals Rule. What Lhopitals Rule says is that in certain cases, like this infinity over infinity, in certain types of indeterminate forms, to find the limit of a quotient like this, you can find the limit of the derivative of the quotients. So I take the derivative of the numerator and the denominator separately. I take the derivative of the numerator, I get 1. I take the derivative of the denominator, derivative of e to the x is e to the x. We're not applying the quotient rule and finding the derivative of our function. We're just taking the derivative of the top and the derivative of the bottom separately. Lhopitals Rule says the limit of our original expression is equal to the limit of this new expression, but you have to have the right kind of indeterminate form for Lhopitals Rule to give a valid answer. Well, can we find the limit of this expression? The top is now fixed at 1. It's a constant. And the bottom is getting larger and larger. It's going towards e to the infinity, which itself is going towards infinity. If the top of a fraction stays constant at 1 and the bottom gets larger, what happens to the overall size of this fraction? A fixed top over a huge bottom, like 1 over 10, 1 over 100, 1 over 1,000, the bottom is getting larger and larger and larger. Well, that means the overall fraction is getting smaller and smaller. So the overall fraction is going to 0, and we've proved that the limit of our original expression is in fact equal to 0, just as we guessed from these outputs that looked as if they were getting tinier and tinier, going towards 0. So this purple graph is a nice, accurate graph of our sketch. And now what I'd like us to do is just summarize what we've talked about in this section. So let's go ahead and summarize what we've talked about in this section. I'm turning to page 13 of this section, and at the top you'll see the word summary. So suppose I'm given a function y equals f of x. Let's remember what f prime of x, the first derivative, tells us about the graph of f. Remember, f prime tells us where the function is increasing and decreasing. Specifically, we said if the sign of f prime is positive, then f is increasing. If the sign of f prime is negative, then f is decreasing. It also tells us the location of the transition points, points between f increasing and decreasing, or decreasing and increasing. And those were what we called the local extrema, and specifically they were the local maxima and the local minima, the peaks and the valleys of our graph. So f prime tells us where the function's going up, where it's going down, and where all the local max and min are. If we want to talk about the steps that we used to figure all this stuff out, remember that we find f prime of x, and then we find the critical numbers. And the critical numbers are any x values where f prime could be changing sign. And we said those values are specifically where the derivative is 0, or what's the other possibility? The derivative could be undefined. If we have a fractional expression for f prime of x, wherever the numerator is 0 will be a place where the derivative is 0, and wherever the denominator is 0 will be a place where the derivative is undefined. Remember, the third step after finding the critical numbers was to throw those critical numbers onto an x number line. And I just kind of generalized it here and said, suppose you find two critical numbers, and I called them C1 and C2. We put a box around those, and those split up our number line into separate intervals, and we just checked the sign of f prime in each of those intervals. By definition, the critical numbers are the only places where f prime could be switching sign. So we just test one test number in each of those intervals. So suppose, for example, we test a number to the right of C2 and we find out that f prime is negative. And then we test a number between C1 and C2 and we find that f prime is positive. And perhaps we test a number to the left of C1 and find that f prime switches sign yet again. In this situation, what would that mean about f? If its derivative is negative, then f is decreasing. And we draw a little schematic diagram by showing an arrow that goes down. If f prime is positive, remember that means that f is increasing. And if f prime is negative, it means the function switches again and f is decreasing. And what would that mean about this point at C1, assuming that the original function f of x is defined there? If the function is going down to the left of it and going up to the right, it must be a low point, if you just thought of connecting these arrows in your mind. And so we would have a local minimum at C1. And how did we find the corresponding y-coordinate for a point on the graph of y equal f of x so that we could actually plot this local minimum? Remember what we did was we took the C1 and plugged it back into the original function precisely because we want a point on the graph of the original function. So if C1 is the x-coordinate of the local min, it's easy to find the y-coordinate. All you do is plug back into the original f. How about C2? What kind of point would that have to be if we just concentrate on this portion of our number line? We said to the right of C2 the function is going down, to the left of C2 the function is going up, so it's going up and then going down. Try to connect those arrows in your mind. This transition point would have to be a local maximum. It's got to be a peak. So we'd have a local maximum at C2. And to find the corresponding y-coordinate, again, you just plug into the original function, f of C2. Okay, so that's what f prime tells us. It tells us where the function's going down, where it's going up, and the location of all the local max and min. What about f double prime of x? What does that tell us about f and its graph? Remember that f double prime of x tells us where f is concave up and concave down. So it tells us a little bit more subtle behavior of the graph, not just, oh, it's going up, it's going down, but how it's going up and how it's going down, what the concavity, whether it's scooped upwards or scooped downwards. So f double prime tells us where the function's concave up and concave down, and the transition points between either concave up and then concave down, or vice versa, concave down and then concave up. Those transition points are called the inflection points. So f double prime tells us about the concavity of f and also the location of all those inflection points. Well, what were the steps to actually figure this stuff out? Well, you have to find f double prime. Remember that it's the sign of f double prime that tells us whether the original function is concave up or concave down. When f double prime is positive, our function is concave up. When f double prime is negative, our function is concave down. So we find f double prime, and then we've got to decide where that expression is positive and where it's negative. How do we do that? Mechanically, it's really similar to what we did up here for f prime. We find what we call the special numbers. It's exactly the same thing as the critical numbers, but they are numbers associated with f double prime rather than numbers associated with f prime. So we find the special numbers, and remember those are places where either the derivative is 0 or the derivative is Okay, now let's think about f double prime of x. What does that tell me about the graph of f? Remember that the second derivative tells us about the concavity of f. Not just the crude behavior, where is it going up, where is it going down, but the more subtle behavior of how is it going up and how is it going down. Is it scooped upwards, concave up, or is it scooped downwards, concave down? So f double prime tells us where f is concave up and concave down. And remember that it's the sign of f double prime that tells us that. So when f double prime is positive, f is concave up. When f double prime is negative, f is concave down. It also tells us the location of all the points that are transitions between concave up and concave down. And do you remember what those transition points are called? It's the location of all, we could fill this in with inflection points. Well, how do we go about step by step finding all this stuff, the concavity and the inflection points? We start by finding f double prime of x, and then we find what are called the special numbers. They're exactly identical to the critical numbers, but critical numbers are associated with f prime, whereas special numbers are associated with f double prime. But mechanically, mathematically, it's exactly the same idea. You're looking for places where the second derivative is 0, or the second derivative is undefined. And if you have a fractional expression for f double prime, wherever the numerator is 0 will make the derivative 0, the second derivative 0, and wherever the denominator is 0 will make the second derivative undefined. Okay, so we find those special numbers. Suppose I find one special number. I called it D1. I stick it on a number line just like we did with the critical numbers, and it breaks up the number line into separate intervals. And D1 is the only place where f double prime could be switching sign. And so I only have to test one number to the right of this and one number to the left of this. So we do our test numbers. Just pick a number in each subinterval, and we check the sign of f double prime. Suppose for a particular function f double prime is negative to the right of its special number and positive to the left of its special number. Well, that would mean that to the left of d1, since we have a positive second derivative, the function must be concave up. And schematically we draw it this way. And it means to the right of d1, since f double prime is negative, my curve must be concave down. By the way, some people like to remember concave up and concave down this way. You notice if I just put 2 plus signs and 2 minus signs, concave up looks like a happy face, and that's nice when you have plus signs for the eyes, and minus signs for the eyes, if you think of that as a face, is a sad face or an angry face, so a frowny face when the eyes are minus signs. So some people like to remember it that way. What about D1? Would that be an inflection point? Is it a place where the concavity is switching? It is. In this case, the way I've drawn it for this imaginary function, it's concave up to the left, it's concave down to the right, so we would have an inflection point right at D1. If the concavity stayed the same, concave up on both sides, it would not be an inflection point. Let's see, so the x-coordinate of my inflection point is D1. How do I find the corresponding y-coordinate? It's exactly the same as it was for the local max and min. To find the corresponding y-coordinate, I want a point on the graph of the original function f, and so I have to plug into the original function f to find that y-coordinate. So I would have an inflection point at d1 comma f of d1, whatever that is for this function. Okay, and if you wanted to, as you go along here, when you do these steps in the first portion where you're looking at f prime, remember that as soon as you get all this information, you can draw a crude graph of f. So right at this point, when we've located the max and the min, figured out where the function's going up and down, we usually go ahead and draw a crude graph of what f is looking like by plotting these 2 points. Maybe c1, f of c1 is a point right here. That is a minimum. and C2, f of C2 maybe is a point right here. It's a max. And just without even looking at f double prime, we know that the function is going down till it gets to its local minimum. And then it goes up until it hits its local max. And then it goes down from there on. And so the function must have this overall crude behavior. When we go through and figure out f double prime and learn about the concavity and the inflection points, we can add that into this graph to get a more accurate graph. So at that point, we can go ahead and say, hey, I can add onto my graph. Here's my C1, here's my C2. I'm just copying the graph that we had. Here's the min, and here's the max. And here was my overall behavior of f. But now I can add the concavity into it. I tried to choose a D1 that was between C1 and C2. So I could choose a D1 that's right here. And suppose that my inflection point is, say, right here. So that's my inflection point, corresponding to the x value of D1. Well, according to my chart here, the curve is supposed to be concave up until I get to that inflection point. So it's supposed to be scooped upwards till I get to this. And then from D1 onwards, for all those x values, it switches and becomes concave down, so scooped downwards. So I want to follow the green dotted line, but I want to do it in a way that is concave up until I hit this red inflection point. So I would try to have my curve going down where it's supposed to be going down, going up where it's supposed to be going up, but scooped always upwards rather than downwards. So I would draw something that looks like this. Here's my minimum, and then it stays concave up until I hit this inflection point. So it's decreasing and increasing, but in a way that is scooped upwards. From that point on, my chart says, oh, it flips to concave down. So from there on, I follow the green dotted line, but with a curve that is scooped downwards. So I would have it go up to its max, and then downwards from there. And notice that my curve is always scooped downwards, but it still is increasing where it's supposed to be increasing, and then is decreasing beyond this maximum. And then we usually added a few more well-chosen points, because often we didn't really have too many points on our graph. And by well-chosen points, we just meant ones that were near the minimums, the maximums, and the inflection points, the interesting things that were happening on our graph. Okay, well that does it for this section on derivatives and how they affect the graph of a function.